Did you just hear my dog bark? You probably did. Okay, sorry about that. And also, from listening to my other video, gosh, I make so many noises. My microphone is so sensitive. Like, I move in my chair, just move my arms. Sorry about all the. Try to make less noises. Oh my gosh. Okay. All right. The definition. Whoa. Whoopsies. Wow. Epic fail. Take two. Okay. The definition of the derivative. Okay. Hey, guess what? Remember when we were talking about the average rate of change? Remember my story about the speeding ticket and we had the radar gun? The radar gun is the instantaneous rate of change. And guess what that's also known as? The derivative. The derivative of a function is the instantaneous rate of change at a point. And so, remember we talked about slope. The slope of between 2 points. Like if I have some function, I have 2 points. I can find the slope of this line, right? That was f of b minus f of a over b minus a. Well, that's 2 points. What we're going to try to figure out is the slope of the tangent line, the slope that just touches at 1 point. And since there's just 1 point, well, we can't use the slope formula. We can't use f of b minus f a or b minus a if there's just 1 point. But what we can do is, wait for it, put those 2 points h units away and let h approach 0. And if this limit exists, well then that's the slope of the tangent line, which is the derivative. There's this thing called the derivative, which is the instantaneous rate of change, the slope of the tangent line. So, hey, that stuff we did in average rate of change, hey, guess what? It's all right here. So we're going to be doing this a lot in this section. Okay, so it says calculate instant rate of change of this function at 2. That means let's take the limit as h approaches 0. So as these 2 points become closer and closer together, what is the y2 minus y1 over x2 minus x1? So algebra is going to be important here. We got to calculus is easy, algebra is hard. So we got to plug in a plus h to the function. Well, that means we got to take a plus h squared minus a squared. Okay, well, a is 2. It said at 2. So f of 2 plus h, well, that's, I guess I forgot to write it. That's 2 plus h squared, right? If we square 2 plus h, so that's 4 plus 2 times 2h plus h squared. F of 2, well, that's 4. So minus 4. So this is this, and this is this. y2 minus y1. And then x2 minus x1, that's h, that distance between the two. Hey, look at this. Here's a plus 4, here's a minus 4. Those cancel, and that always happens. And hey, guess what's left over? These both have h in common, so factor that out. If I take h out of 4h, there's 4. If I take h out of h squared, there's h. So just distribute this back. Is that 4h? Yes. Is that h squared? Yes. And look at this, repeated factor, top, bottom. And we know from limits, oh, that's why we use limits. That this limit will exist. This is a whole. And what's this limit as h approaches 0? 4. What's 4 plus 0? It's 4. So that means if you were to graph y equals x squared, which I've crudely done here, and if we went over here to x equals 2, oopsies, if we went over here to x equals 2 comma 4, the slope of this tangent line is 4. And that's what we're talking about. And now we got a whole bunch more examples. Here's this one here. So I might just not talk much. I might just kind of, you pause and kind of go through. So basically on these next few pages, here's the function. And we just need to do this. So plug in x plus h to the function. That's kind of this step. Follow through there. And then do the second part. Take f of x plus h minus f of x. So that's this part. Then prove the quotient, which is the factoring. Cancel, limit. Okay, so pause that, go through that. This one here, same exact setup. just a different function. So here's the function. So we're going to take x plus h plugged in for x. Sometimes the way I like to think about it is we've got something squared plus two somethings. That's what the function says, right? Something squared plus two somethings. Well, then we got to distribute this out and distribute this. Well, x plus h squared is this. Two of these is these. And then minus the function. Just don't forget your parentheses, because it's minus this, minus that. And again, this will always happen right here. Here's an x squared. Here's a negative x squared. Here's a 2x. Here's a minus 2x. And guess what all these other things have in common? They all have an h in common, which we can factor out. And then those cancel. And then this limit is 2x plus 2. So here's a function for the derivative. F prime is 2x plus 2. Well, what's f prime 1? We'll plug in 1. 2 times 1 plus 2. What's f prime 2? Plug in 2. 2 times 2 plus 2. What's f prime 3? Plug in 3. 2 times 3 plus 2. All right, same deal. Just a little different function here. Okay, so the function is 3 something squared minus 4 something plus 5. 3 something squared minus 4 something plus 5. And then minus the function. So minus this, minus that, minus that. And so now here's a 3x squared, here's a minus 3x squared. Here's a minus 4x, here's a plus 4x. Here's a plus 5, here's a minus 5. And everything that's left has an h in it, which then we can factor out h. We can factor out this h, cancel, and then take this limit. And just follow through the rest here. Plug in these numbers to this derivative. Very similar. Step through here, okay? It's the same exact quadratic kind of function. Okay, so just step through the algebra. Okay. This is a good page. So, there's a lot of ways to notate the derivative. A very popular way is to say f prime. So this little symbol here, apostrophe, you read that as f prime. That means the derivative of the function f. That means the instantaneous rate of change. That's the slope of the tangent line at a certain point. So function derivative. There's other ways you could write it too. You could say dy dx. Now, what the heck's dy dx? Think about other d words in math. How about delta y over delta x? Hey, that's like slope. Rise over run. Change in y, change in x. So you can think of dy dx like that. This here is like an operation. Here's a function. This means, hey, perform the derivative upon that function. And here's another way to think about it. We'll talk about this notation kind of later. Y prime, that's like the rate of change of y, which f prime, f of x and y are the same, so f prime, y prime are the same. Okay, so now, not all the time could we actually do this. What do you mean? So are there functions that don't have tangent lines at a certain point? Well, look at this function here. Right here, how about when x is negative 2? Is there a tangent line? Well, no, there's not. There's not one tangent line here at this point, and there can't be a tangent line when there's no function. And so continuity and differentiability are related, but it's not 100%. So look down here, it says, when is this function not continuous? Well, yeah, negative 2, 0, and 2. Right? If I have to pick up my pencil, so this one fails the limit not existing part. This here fails the not defined part, and this fails the not defined part. Okay, when is it not differentiable? Well, okay, all of the place where it's not continuous, it's not differentiable. But then also look here. There's a sharp corner right here. Now, anywhere else on this function, like right here, at this point here, I could draw a tangent line, right? Like right here, I could draw a tangent line. Even on this straight line part, I could draw a tangent line. Like over here, I could draw a tangent line. But what about on this tippy top point there? Is there one tangent line there? No. It'd be like a teeter-totter. I could draw a tangent like this, I could draw this, I could draw this. And that's no. So we would say that right here at x equals 5, it is not differentiable because there's not one tangent line there. So differentiability, get all the non-continuous parts and also look for like a sharp corner, or like a cusp. Sometimes we'll say that word cusp. All right, here's some other examples. So same kind of deal. So first of all, when's it not continuous? Well, yeah, here and here. So when's it not differentiable? Well, those places, all of the places it's not continuous is also not differentiable, but also look here at 2. There's a sharp corner. So think about a 2x4. Anywhere else in this picture, I can lay my 2x4 down and touch the graph once. I missed a little. Like right here, I can make it, oh, that was bad. Do you see what I'm trying to draw? There we go. Tangent. But right here, there's not one tangent line, so it's not differentiable right there. And then same thing with this last one here. When is it not differentiable? Well, any of these times where it's not continuous, it's not differentiable. And then any of these sharp corners is a problem. But anywhere over here where it's nice and smooth, yeah, that's fine. I could lay a tangent line on there anywhere. And on an actual line, the tangent line would just be concurrent. All right, so that's the derivative.